Hello everyone, I'm Rabab Abdelfattah and today I will give a talk on partial label momentum curriculum learning for multi-label image classification. So let's start by talking about different settings for multi-label image classification. As shown into this figure, we have two different main categories, fully labeled category and partial label category. In the first category here, all positive and negative labels are annotated of the dataset, such as full set fully labeled setting, or subset of images are fully annotated while the remaining images are totally unlabeled, such as subset fully labeled setting. This setting is usually used in semi-supervised training model. In the second category, partial of positive and negative label are annotated. We have different settings. In the first setting, at least one positive or negative label is annotated in the whole images of the dataset. While in the second setting, only one positive label must be annotated in the whole images of dataset. To go one step further, we introduce a new partial label setting of subset single positive label, where the subset of labeled image is annotated with only one positive label on each image, and the rest of the images is totally unlabeled or unobserved. The main goal of our new purpose setting is to relieve the annotation burden. We developed an end-to-end training model as multi-label classifier under the proposed new partial setting. Additionally, our model can be easily to extend to handle other partial label setting for multi-label image classification. So, according to related work, early work on multi-label image classification assumes that the unobserved labels are negative. However, depending on this assumption, the possible performance drops by incorrect initialization the label. Another work here was depending on building the graph between the images and similar label. However, this model is not applicable for single positive label setting and also for our purpose setting. Another work addressed the partial multi-label image classification based on the curriculum learning. However, they depend on threshold-based strategies, which lead to, first, lack the continuity. The second issue is the information loss, which comes from some pseudo label may never be selected for the network training. And finally, updating pseudo label without a clear goal. So now let's introduce our framework. Our model addresses the most challenging setting, SSPL. As you can see into the figure, we have two subsets of the images. The first subset is annotated with only single positive label, while the other group of images is totally unlabeled. We will use the pseudo label to guide the network for the unlabeled data. The main target of our framework is how to update the pseudo label. Our framework is trained alternatively between updating the parameter of the network and updating the pseudo label, as I will explain into the next slide. I will start first here talking about the updating of pseudo label by the momentum. The momentum comes from the aggregation of the gradient of loss function to find the right direction for updating the pseudo label vector. As you can see here into this equation, the first term represents the aggregation value of the momentum, where we initialized the momentum value with 0 at the beginning of the training. The second term here is the gradient of the binary cross entropy between the prediction and pseudo label, as you can see here. Therefore, when one entry of the momentum vector moves toward the same direction, the estimation of the association pseudo label will be more confident, and the variation can be well smoothed over consequence of epochs, which leads to a more stable training behavior. Additionally, we need to introduce the self-guided momentum factor to control how much momentum should be used to update the pseudo label. As you can see here into this figure, when the confidence of the pseudo label for a class is low, we want the corresponding momentum to contribute more to the pseudo label iteration in order to drive the pseudo label away from its current value to avoid undesired local minima. While if the pseudo label have a high confidence level, so we need to keep the current value of those pseudo label without too much contribution from the momentum. So based on the self-guided factor and momentum value, we can update the pseudo label latent parameter as shown in this equation. Then we need to normalize the pseudo label latent parameters using the sigmoid. During this stage, we fix the prediction vector and just we need to update the pseudo labels. The second stage of our framework related to the updating of parameter of our network. We use this loss function, which consists of two parts. The first part is binary cross entropy classification loss between the observed label and the association predicted label. The second term here is the cross entropy classification loss between the pseudo label for unobserved label and their associated predicted labels. However, we used the scheduler curriculum learning to balance the contribution of the unobserved label to the total loss, and also we need to avoid the negative impact of false pseudo label into our total loss. As shown here into this figure, when the pseudo label has a low confidence level, the scheduler will assign a small weight to the total loss, which will not be significantly affected. This is especially important at the beginning of the training process when the pseudo labels are still not indicative. During the iteration, the pseudo labels start gradually building up their confidence, and consequently their weight into the total loss function started to be increased, so that the scheduler plays the important role to manage using the pseudo label based on their confidence during the training process. According to experiment result, we did our experiment on 3 different datasets: Pascal dataset, Coco dataset, and NUS dataset. According to implementation details, we used the same backbone architecture and the same classifier for all the comparison, and also we reported our result based on best mean average precision on the validation set for all the model reported into our table. Into this table, we reported our result based on the full set single positive label setting and compared our result with the state-of-the-art model. Above this line, the model are trained based on fully labeled data and compared with the other model just are trained on single positive labels. As shown here into this group specifically, we can see that our model outperforms the other loss function under single positive label category. From the other point of view, for example, in Coco dataset, in fully labeled setting uses about 100% of the annotated labels, while into single positive label setting uses only around 1.2% of the total number of labels. It's worth mentioning that the mean average precision of our model under single positive label remain comparable to mean average precision result in fully labeled setting. Also here we reported our result based on subset of single positive label setting. As you can see here, 20% means that only 20% of the images of dataset contain single positive label and the other images are completely unlabeled. As you can see here, into 3 different datasets, our model outperforms the other losses based on momentum curriculum learning. Also, we compared our method here with the state-of-the-art semi-supervised method, such as fixed match and UPS. As you can see here, that our purposed model always outperforms the other two methods during different subset of single positive label setting. This is because fixed match and UPS are trained based on the supervised loss over the set of observed label, while ignoring the unobserved label of the labeled set. Therefore, there is like a lack of continuity in pseudo label updating. On the other hand, our purposed model can guarantee the continuity and capture the temporal information during the training. So it's not surprising that our purposed model achieves the best mean average precision scores. So finally, we present the application study for our purposed model. As you can see into this table, we start with the basic variation of the model, which uses the cross entropy loss on the observed label. In this case, we assume that all the unobserved labels are negative, since ignoring the unobserved label may lead to overfitting during the training. When adding a component into the model, this assumption will be removed, since we use the pseudo label to deal with the unobserved labels. We first add the momentum generation module to update the soft pseudo label, which improve the mean average precision for different settings in Coco dataset. Additionally, when we add a confidence-aware scheduler and self-guided factor, we also have like improvement into overall performance, since they work together to make the training adaptive with respect to the confidence of pseudo label. So finally, let me summarize my talk today. We introduce a new model for multi-label image classification under partial label setting. In our purposed model, soft pseudo labels are generated per image and then updated based on the momentum and the confidence level. Extensive experiment demonstrates that our purposed model outperforms several state-of-the-art methods. Our purposed model is generic to all kinds of partial label setting. Thanks for your attention.